Hello, welcome to Reusing Washing Machine Motors the Simple Way, Part 2. This is, as the name implies, the second part of the series, but I have made one other video just before that also deals with this topic. So I recommend you to watch both that video and part 1 to the series before watching this one, and as always you can find the video links in the video description. But let us just briefly sum up what we saw in the last two videos. In the first video, I performed a series of experiments around induction motors and universal motors. We saw that the frequency of revolution of an induction motor is directly dependent on the frequency of the AC supplied to the motor. We then saw that a universal motor, like this so-called washing machine motor, does also spin up, but that the frequency of revolution is going up and up and up and is not directly related to the frequency of the grid. In the second video I then presented or tried several methods to stabilize that frequency of revolution. We saw that both a simple variac and a non-regulated phase-fired controller are not the answer. As a third and the only viable solution so far, we saw that a thyristor-based controller can be realized that stabilizes the frequency of revolution by means of stabilizing the back EMF induced in the universal motor. That circuit, however, had some drawbacks as well, one of them being that it is just a half-wave design that limits the maximum power that we can distribute to the motor. In this video I will present a full wave circuit that will solve that problem as well. But before I go on with that, let me address some safety concerns here. In the last video I used basically my hands to load the motor, and what I did is, for example, to touch the transmission belt that I have now removed for this experiment. And of course I was giving a very bad example there, and I don't want you to repeat that at home. I basically went down a dangerous way there because I was working on a handbrake system, couldn't get it ready in time, so I did it like the quick and dirty way. But do not do that. In this video I will not use the transmission belt at all, but use this part here which I salvaged from an old bicycle brake to put some load on the motor when needed. Another little thing that I want to talk about before I go on is a mix-up that some people had between two different things on two different levels. Now I used the term frequency of revolution and used FREV as a symbol for that to describe how fast the motor axle or motor shaft is spinning. Some people thought that that is wrong and that this quantity is called revolutions per minute and is measured in RPM. Now the problem here is twofold. First of all, revolutions per minute cannot be a viable physical quantity because it is directly derived from a unit of measurement, the minute. So what the RPM is a unit of measurement for a quantity called frequency of rotation. And if you don't believe that, just go on Wikipedia, type in revolutions per minute, and here you have it black on white. And the second mistake that people made here is to mix up units that people just use without thinking about it, or maybe in the US and here in Germany and in scientific projects, for example. And the thing here is that RPM is not only not a quantity, but also not a unit of measurement in countries where the metric system or the SI is used. In Germany we use 1 per minute or 1 per second, which is the same as 1 Hertz. And let me just read out loud what we find in the Wikipedia article. And here it says, revolutions per minute is a measure of the frequency of rotation. There you have it, black on white. And down here we have a paragraph about the International System of Units, which you guys maybe call the metric system. And here it says, According to the SI, RPM is not a unit. This is because the word revolution is a semantic annotation rather than a unit. The annotation is instead done as a subscript of the formula sign if needed. Because of the measured physical quantity, the formula sign has to be F for rotational frequency and so on. The corresponding basic SI-derived unit is s to the power of -1 or Hertz. So as you can see, okay, I used FREV and frequency of revolution instead of rotation, but yeah, the important thing here is that you use F because that is the symbol for the quantity frequency which is expressed here. And just to make this clear, I don't have anything against RPMs or any other unit that is used in English-speaking countries, and I don't want this to be a battle of systems of measurement. Quite the opposite. What I have done in the last video is to use quantities rather than units of measurement for most of the time. I said when the voltage across the universal motor goes up, so does the frequency of revolution. So I'm not even using a specific unit system here. What I'm doing is to describe dependencies of physical quantities, and units of measurement have nothing to do with that. And I am now at one of the other workbenches, and what I have set up here are a couple of the control boards that I have salvaged from actual washing machines. And I did this because I wanted to address a question that has been brought up by several people in the comments section, and that is the suggestion, why not simply to reuse the control boards from inside the washing machines? Well, at first glance you can already see that these boards are way more complicated than everything that I'm going to show you in terms of new builds. And frankly, the complexity of these circuits is way above what the vast majority of the viewers can understand, not even to speak about reusing and modifying these boards. Then you can also see that we have a large variety, even within models of the same manufacturer, completely different styles of the circuit boards. Also, the circuits will be quite different. And how could I ever give general advice about how to modify these circuits if they are so different? Then you can also see that, for example, on this Siemens board here, there's way more going on than just the motor control. You have different ports here where things like electromagnetic valves, the pressure switch, temperature sensors, a front panel with LED 7-segment displays, and so on are connected. So there is way more going on than you actually need, and that adds a lot of complexity to an already complicated problem. Then, on top of that, and maybe the most devastating problem of them all, is that these companies, of course, try to keep some of their knowledge hidden. The devices, these chips that you can see here, are not off-the-shelf components where you can just look up the datasheet online and find out how to reprogram them, if they are even reprogrammable in some cases. And yeah, these devices, for example, are made by ST but branded as Miele parts. These are microcontrollers manufactured by the Motorola Corporation. And if you look up the parts numbers, you find nothing anywhere on the internet. And I have a hard time believing that there is a large number of people outside of the actual developers of these boards who really know how to repurpose them, or who could know that. So in other words, this is just not a viable way. What I recommend instead is to salvage the larger components that you find on the boards, like the relays, the triac, and some of the more chunky components of the power supply circuits, and then basically dispose of the bare boards. You can then use some of the capacitors, the triac, and so on to build your own motor controllers. You can also use this to build small power supplies for your own design. Some people have been telling me in the comments section that there are still washing machines that use separate boards with quite simple motor controllers that can easily be repurposed. So if you have something like that lying around, make a photograph of it and upload it to the internet. Provide a link in the comments section so that we can see where we can get that. Please also add make and model of the machine from which that circuit was salvaged. So before I will start with the actual building process, let us take a closer look at some of the specific parts that I'm going to use here and also address some safety concerns. First of all, this is the type of enclosure that I will use here. And in comparison to the two other enclosures I used so far, this one is different in that you can plug it directly into your socket. It then has another socket on top where you can plug in the motor. This design is very safe in that it is completely insulated from the circuit that will be inside. This will reduce the chance of you coming in contact with a conductive part that carries a voltage in reference to the earth ground. And that means that this circuit that we will use here does not have to be isolated from the grid. And if you have a hard time understanding the difference between electrical insulation and electrical isolation, then I urge you to watch my video about the power grid, in which I explained these terms, also what an RCD or GFCI is, how it works, what kind of health hazards there actually are when you handle voltages from the grid. So just to repeat it here again, the voltage supplied by the AC line coming out of your wall can kill you. And at least that video that I will link in the video description can give you an understanding of what these dangers actually are. We will build the circuit on this board here, which is called a perf board or a vero board. We will of course only lead a small section of it. And this is a technique that I have been using for the last years almost daily. In most of my videos I use this to build up prototypes, and that it is what it is good for. It is not a good technique if you want to reproduce your circuits in great numbers, but if you just want to build one of them, it's still the best way in my opinion. But I'm a little bit old-fashioned there. This potentiometer is also a quite uncommon component these days because it is a wire-wound potentiometer. You will need a potentiometer like this because it is rated for a quite high power dissipation. You cannot use your normal potentiometers. You need a wire-wound one for a power rating of at least 1 watts. This specific potentiometer costs somewhere between 3 and 5 euros. But at least in Germany you have the possibility to buy a set of these older, cheaper wire-wound pots here, and I will put a link to that in the video description. The next thing that we are going to talk about are thyristors. This is a thyristor like the one we will use in this project. You need one that is at least rated for 400 volts if this is operated on a 230 volt grid, and for let's say 5 amperes like in the last circuit. And the first thing that I have to do is to shorten the shaft of the potentiometer because it's actually about 2 to 3 centimeters too long. And I just do that with the help of a hacksaw. And when building a prototype like this for the first time, it's a good idea to take the most chunky components, like here our wire-wound potentiometer and this little compartment for a fuse, which is just penetrating very deeply into the enclosure, to install them first and then see how you can fit the PCB in the remaining space, where then the smaller components that take up much less space can be cramped in. And in order to install the components, drilling a couple of holes is of course part of the game. And as you can see here, there's often a tiny tooth on here that is supposed to prevent the potentiometer from slipping away in this direction. And that is why you need another small hole, or indentation at least, in which that tooth can grab. And with these holes being drilled, you can then install the fuse compartment and the potentiometer, and you can simply fasten them by bolting them in place. And with these parts being installed, you can then roughly see how much space actually remains inside the enclosure. And as luck would have it, there are these 4 mounting posts here, in which I could simply screw in these self-tapping screws, This is the type of screw that you can find in the enclosures of ATX power supplies, by the way. And I will now prepare the Vero board to be screwed on here, and then we will populate that with our electronic components and so on. But before I will go on, I first need some kind of heatsink, and for that I will use a piece of aluminium angle plate like this one, and I will simply cut off a section with a hacksaw and then drill some holes through it with a drill press. When you install parts on a heatsink, you have to think about if there is maybe an electrical connection between the parts that you don't want to have. Now, this bridge rectifier is already insulated, so all you basically would have to do is to apply some thermal compound that you can get in different forms, as you can see here, and really just a thin film of that, and then bolt that to the heatsink. But for example, with this triac, where you have a conductive electrode as the heatsink on here, you have to use a little insulating plastic washer and a piece of insulating silicone sheet to insulate the cooling surface from the heatsink. And according to the datasheet of the manufacturer of these silicone sheets, it is not necessary to add additional thermal compound to this. So, and with the heatsink and those two parts installed, we can then proceed with the other components. And the part that I'm adding here now is one of the less elegant parts of the circuit. It's a 5 watts power resistor that you need in order to derive a reference voltage directly from the 230 volts AC line. And this thing, of course, dissipates quite a lot of heat, and that is why you need these little tubes here to put some kind of distance between the resistor and the board. And with all components soldered to the board, tin-coated copper wire is used to make connections between the leads of the single components. And the next step is, of course, then to connect the external parts here to the board with wires. And of course, last but not least, inserting a fuse into this fuse compartment. Now we only have to screw it all together and test it. So as I said in earlier videos, it is not safe to run a series wound self-excited DC motor like this without a load at the full line voltage, and that is why we will use this old power drill here to test the circuit before we connect it to the washing machine motor. So this video shows us 3 things about this modified full wave version of the control circuit from the last video. First, it can be used to adjust the frequency of rotation of the rotor shaft. Second, it can be used to stabilize that frequency independent of the load applied to the rotor shaft, at least within certain boundaries. And third, if the voltage from the tap on the potentiometer is turned down to a quite low value, the regulation doesn't work anymore. The attached motor starts to stutter. And maybe you could say fourth, it is apparent that this circuit can only be used to regulate the motor at rather high RPMs, so to speak, at a rather high frequency of rotation. And it might just be that it is not suited to regulate the washing machine motor down in the low revolutions per minute or low frequency of rotation that we actually wanted to have. Okay, so moment of truth. So at least for this application, the new modified full wave circuit is pretty much a failure, and you could see that by reading off the values from the DMM. 300 to 400 Hertz, that equates to 18,000 to 24,000 revolutions per minute, basically immediately after switching the circuit on. And that means that this circuit tries to regulate the back EMF, but fails so if we want to have a quite low back EMF that would result or correspond in a low frequency of rotation. So either the circuit has to be modified or another approach has to be chosen to use this at full power for a washing machine motor. So I would say let's just take a quick look at the modifications that I made to the circuit from the last video, and then let's see how we will proceed. This is the half-wave circuit that I worked with in the last video, which delivered reasonable results. For this video I basically inserted a full bridge rectifier into this circuit so that this little diode here then could also be removed. This resistor here that was connected in series with the potentiometer was also temporarily removed so that I could try to derive lower voltages from the tab on the potentiometer in my experiments. I also tried many different variations of this circuit. For example, I eliminated this whole heating resistor voltage divider thing and used a separate isolating power supply to derive the triggering voltage for the thyristor. I also changed around some of the resistive values, tried better filtering and so on, added capacitors and snubbers here and there to see if I could influence the result of the performance of the circuit. And I spent the better part of 2 days doing that, but I simply couldn't get this circuit to perform the way I wanted. I then also went for a completely different design that used similar parts, but had, in addition to the thyristor, also a primitive amplifier circuit that was made up of 2 discrete transistors. I was also working on a circuit based on the TCA 785 integrated phase-fired controller, a component that is still manufactured but rather expensive. The circuit around it is also quite complicated. I also bought a TDA 1085C, which is an integrated circuit that once was manufactured for the sole purpose of driving motors inside washing machines. The problem with these devices, however, is that they are no longer manufactured and they are very rare and expensive. As a matter of fact, I only could find one guy who as a private person still sells some of these, and it's just some parts that he has still lying around, and he charges about $10 per piece, and I don't know how many he has even left. So I figured that this wouldn't be a good base for a video made in the year 2016. But I will realize that circuit, and I guess that you will see that in a future video. And here you see me testing a circuit that I built around a Telefunken U208. It's an open loop phase-fired control circuit that I could get for little money. Problem here again is that these types of circuits were manufactured by Telefunken, a company that does not exist anymore. And the U208 as well as the U209, 10, 11 and so on, all of which were like wonderful integrated motor control circuits, are obsolete now. And here you see me working on a circuit built around the TL494 switch mode power supply controller, a very cheap and abundant device that I hope could be used to control the motor as well. But this circuit will also be capable to act as an interface for a microcontroller platform that can be used to switch either the IGBT or the MOSFET that is installed on the heatsink of this board. I want to try to compare the performance of the two devices in this regard. But here another problem has emerged, and that is that all the other devices that I have built to this point are supposed to be installed inside a plastic enclosure that insulates the circuit from the outside. But as soon as people would try to connect their external devices like Arduino platforms or other microcontroller platforms to this circuit, there would be a rather large health hazard here, because you cannot simply connect your non-insulated Arduino board that is just lying around your bench to a circuit like this that is directly fed by the power grid. So at this moment I really cannot deliver a circuit that is both safe, working, and based on a non-obsolete device. And that is why I would recommend you to use the circuit from the last video until I come up with something better. And what I recommend you is to use the building techniques that I showed you today and apply that not to the full wave circuit but to the half wave circuit. It's exactly the same thing. The components are to 90% identical. But in order for you to apply this, there is still one more thing we have to talk about, and that is the actual pin out of the motor from inside the washing machine. And let's take a look at that just now. Okay, so here we have our assembled motor, and next to that some parts that I salvaged from another washing machine motor, and then we have a third motor over here in the corner. What we will do now is to take a look at the 7 leads that are leading up to this motor or that are coming out of it, and then I will step by step explain what these leads are good for and what you will need to know about them. So first of all, the first thing that many people wonder is, why do these motors not just have 2 pins like the normal DC motors that I know? Well, the thing is, this is a DC motor, but it doesn't use a permanent magnet to create the stator field. A motor that uses a permanent magnet is often called a permanent magnet DC motor. In German you would call such a motor permanent erregt, which means permanently excited. Yes, sounds stupid. Believe me, it also sounds stupid in German. But a motor like that is permanently excited because a permanent magnet is used to create an outer field in which the rotor spins. But when you want to use such a motor with AC, it is not only the field inside the rotor field that has to change direction, but also the stator field that periodically has to change its direction. The idea is basically that each time the polarity of the voltage across the rotor is reversed, it is also reversed across the stator. And only when that is done, it is possible to use a DC motor with AC. Okay, maybe this is something we would have to talk about in a more theoretical video at some point. But most of this stuff can be learned by watching my video about brushed and brushless DC motors, the link to which I will put in the video description. Now, the rotor itself is connected via the copper contacts here on the so-called commutator to the commutator brushes that you find inside this piece that is made of a cast aluminum alloy. These carbon brushes here make contact to the commutator and lead out of the motor. Here you can see these brass contacts on the left and on the right, where 2 leads would lead out of the motor. And that accounts for 2 of the 7 leads that are coming out of here. And these would be the 2 leads that would come out of a permanently excited DC motor as well. And if you want to write that down in terms of symbols for a circuit diagram, you would simply draw something like this. It's basically a circle with an M inside, and then you have these 2 black things here, which, as far as I know, remember you of the carbon brushes. Okay, so that is the symbol for the rotor. But since you have also a stator winding, or in this case actually 2 stator windings, you also have 2 windings here that are just drawn as inductors. Okay, so what is done in a motor like this is that the field windings, which are also in this case connected together, are connected in series with the rotor. So that would account for 1, 2, 3, it's actually
5 of the leads, because the rotor and the stator are not connected together inside the motor, but are being connected outside. And that is done in order to provide the possibility to reverse the direction of the motor when it is used with AC. Now, most of you know probably that a permanently excited DC motor with permanent magnets can simply be reversed in its rotational sense by changing the two poles, right? By reversing the polarity. Now, if you use AC, that is not possible because the polarity of the AC changes by itself 50 times per second. So what you have to do is to connect the field winding to the motor in another way. That would mean to not connect them down here, but to connect them up here and then connect this here to the grid. Okay? So if you want to reverse the direction or the rotational sense of a universal motor that is powered, in this case by AC, you have to use relays to switch the field windings in series with the rotor, but, you know, the other way around. Okay, so you have 2 leads coming from the rotor, 3 leads coming from the field winding. And what you can do is you can use the entire field winding or just half of the field winding by connecting the grid to the one end of the rotor and the center tab or the tab of the field winding. Now, that will result in a strengthening or weakening of the stator field that is generated by the field winding, which will then lead to another behavior of the motor. And I don't want to make give a general advice about that. If you find a washing machine motor like that, you can try to use the half of or the entire field winding and see how the motor will respond in your particular case. I mean, I could tell you how it responds, but the question is if it makes sense in your application. This is not rocket science, just try it. Okay, so this accounts for 5 of the 7 leads. What we then have on the rear end of the rotor shaft right here, encapsulated in this black plastic, is a generator that is tied to the rotor. It is called a Tacho generator or Tacho coil because it generates an AC voltage that is not used to supply an electronic circuit with energy, but to read out a multiple of the rotational frequency of the rotor shaft. Now in this case, and I guess in many other washing machines, the frequency of the AC generated by this Tacho generator is exactly 8 times that of the rotor shaft. So if the rotor shaft is spinning, let's say at 600 RPMs, that would be 10 revolutions per second, then you would have a readout of 10 times 8 Hertz, so 80 Hertz would be the frequency of that. Now, you don't need the Tacho generator to power the motor, but it is used as a feedback signal inside the washing machine to keep the motor running at a constant rotational frequency. Now I have tried to show you a circuit or a solution based on that circuit in which you do not need the Tacho generator because the so-called back EMF, which is a voltage that is induced across the rotor, is used as a feedback signal. So the idea here basically is that if you want to try this the way I did it, you do not need the Tacho generator and you simply have to connect the field winding and the rotor winding in series. Then you will effectively only have 2 leads and you will be able to connect these 2 leads to the circuit that I've shown you. Now for the examples that I used until now, I didn't need the Tacho generator, either because I used the back EMF or I used the signal from this Hall effect sensor that I added to that motor. In my opinion, a Hall effect sensor is a better solution for many modern circuits because it already delivers a DC output signal that is rectangular in shape and can be easily read out by a microcontroller, for example. But its resolution, so to speak, is of course smaller than that of the Tacho generator, which basically delivers 8 pulses or 16 pulses if you rectify it in just one period, one revolution. But yeah, this Tacho generator will be used in the TDA 1085C circuit that I still want to experiment with. Okay, so here you have a better, more complete version of that drawing which I just made. And you can see here the 7 pins where the 7 leads go. 3 for the field winding, 2 for the rotor, and 2 for the generator sitting on the rotor shaft. And of course there will be different topologies somewhere around the world, but I'm sure that the majority of washing machines also in other countries will be based on a variation of this basic topology. Okay, so now you have a basic circuit and the basic knowledge of the pinout of the motor, and that should give you the possibility to experiment with these just as I did. And yeah, maybe I will complete those more complicated circuits and come to promising results in the future, and then of course there will be another video about this. But at this point I'm really promising nothing. I guess I will show you more about this, but I guess the next video will be about another topic first. So no matter what, I hope that you like this and I could help you out maybe, and I hope to see you soon.